Alright, we're going to look at how to do least squares regression. This is all about finding the line of best fit for some linear data. So we're going to split this into several different sections. The big thing that we're going to talk about today is interpreting a regression line. What does it mean? What does it tell us? What can it tell us? And what can't it tell us? So a regression line summarizes the relationship between two variables, but only in settings where one of the variables helps explain or predict the other. So this equation is for if the explanatory variable influences the response variable. They have to be dependent on each other. They have to explain, one has to explain, the other one has to predict the other. So maybe the length of someone's foot and their height. That would be an example where we could use a regression line. So it's a line that describes how a response variable y changes as an explanatory variable x changes. We often use the regression line to predict the value of y for a given value of x. So in the textbook that we use, we have this scatter plot. It relates the amount of non-exercise activity, so fidgeting and things like that, and the measured fat gain after 8 weeks. So each point represents a person, and this non-exercise activity we're hoping explains the fat gain. We're hoping that it predicts the amount of fat gain. And we can see that it has negative correlation. It's fairly strong. And we have a regression line in red drawn in there. We can use that line to predict the amount of fat gain for a person. For instance, when somebody's non-exercise activity is 800 calories, we can predict that about 0.8 kilograms of fat gain will have occurred. So we go up to the line from our explanatory variable over to our response variable, and that is our predicted value. So this is a model. This is modeling what's happening. It's not a perfect explanation. It's just giving us an idea of what's going on. This sentence is kind of important here. The equation of a regression line gives a compact mathematical description about the response, about the relationship between the response and the explanatory variables. So here is the way we write this equation. Suppose that y is a response variable, x is an explanatory variable. A regression line relating y to x has an equation of this form. Notice that it's not y equals, it's y hat. It has a caret on top of the y. That is standing for the predicted value of y. We don't know what y is. We're predicting that this will be the output. So it is important that you use this notation when you're writing a regression line. Y hat equals a plus bx. Or you might see it y hat. You've seen mx plus b. You've seen bx plus a. I think your calculator gives that as a way of writing it. You might see in your formula book b sub 0 plus b sub 1 times x. It doesn't matter what notation is being used for our slope-intercept form. The number attached to the x is our slope. It is our amount by which y is predicted to change when x increases by 1 unit. This is important. When explaining what the slope means, you're saying, when you're interpreting it in the context of the problem, you're saying that our response variable is predicted to change by this much when x increases by 1 unit. Important piece right there. But that number attached to the x is our slope. The constant is our y-intercept. It doesn't matter what the letters are that are stuck in here. You should know what they mean. Whether it's A or B or B1, B0, it doesn't matter. Know what they mean. And that y-intercept, the A, that's the predicted value of y when x is 0. So there we go, nothing new, just a little bit different notation and being a little bit more precise with our vocabulary. Change when x increases by 1 unit. The predicted value of y. Those are words that you need to start using. So here we go, consider the scatter plot again. Does fission keep you slim? Identify the slope and y-intercept and interpret each value in context. So here's our y-intercept, and we'll talk more about how to find this later on, but I'm telling you that A is 3.505. Our slope is negative 0.00344 times the NEA change. We could and probably would see this written as y hat equals 3.505 minus 0.00344x. They're using words instead of variables, and that's okay. So here's our regression equation. What do the different pieces mean? Well, the slope of negative 0.00344 tells us that the amount of fat gained is predicted to go down by that many kilograms for each added calorie of non-exercise activity. Notice the words that we're using here, people. The amount of fat gained is predicted to go down for each added calorie. And then not only that, we're using what the things mean. So instead of y changes, the predicted value of y changes, it says amount of fat gained. That's what y really means. Predicted to go down, that's the negative, by that number for each added 1 calorie of non-exercise activity. So you have to use good words. That's what it means when it says in context. What does the y-intercept mean? Well, that means that the fat gain estimate, the y-intercept of A equals 3.505 is the fat gain estimated by this model if the non-exercise activity doesn't change when a person overeats. So back to the basic problem here, back to what this thing was discussing or looking at. The researchers overfed 16 people and then increased their non-exercise activity. So in this problem, for the person that doesn't have any change, they'll gain 3.505 kilograms of fat. That's our estimated fat gain. Interpreting this point, somebody who had an increase of 700 calories in their non-exercise activity would have 1.5 kilograms fat gain. So there's our interpretation. Be precise with the vocabulary that you're using and what things mean. We can use regression lines to predict specific, or to predict y values for specific explanatory variable values. So for instance, if I wanted to know what would happen based on this model if I increase somebody's non-exercise activity by 400, we can use this model, we can use this line, we can use this equation to figure that out. So here is our regression model. We plug in 400, better than just going up to the graph and over, that's an estimation. We can see it's going to be a little bit bigger than 2 kilograms. Crunch the numbers, we get 2.13. So now we state this as an answer in the context of the problem. So we predict a fat gain of 2.13 kilograms when a person with non-exercise activity is equal to 400 calories. Again, in the context of the problem. And the last thing we'll talk about here is something called extrapolation. We can use the regression line to predict response values for the explanatory variables x. The accuracy of this prediction depends on how much data scatter about the line, so how good of a line our data makes. For data values close to our data points, we can substitute values of x. We can substitute any value of x that we want, really, but when we go outside the observed values of x, that's called extrapolation. And when we go too far outside of what we observed, we observed values of x from -200 to 800. We can't really say what's going to happen if it goes out to 1,000. If we plug in 1,000, we don't know if that point will fit our data. We don't know if that will fit our model. Those predictions usually aren't accurate. So don't make predictions using values of x that are much larger or much smaller than those that actually appear in your data. And that, ladies and gentlemen, is where we stop for today. Have a wonderful, wonderful day.